So I thought it would be better, instead of me continuing to talk, to show a demo how it looks like and how it works. Can everybody see this? Do I have to enlarge the font?
Move the terminal over.
Oh, sure. Sure, I'm going to have to resize it anyways because I want to put. Right. I just realized I should have done this beforehand, but bear with me for a second. So okay, so what I want to do is I want to show you a cluster which consists of 4 nodes. So 1 master and 3 workers, and this is obviously going to be on my local machine, but it would look the same, like for example if you just use like Amazon cluster or whatever you have. So I'm first going to start the workers. As I said, the order doesn't really matter. So what we have here is I just have the shell script that starts the worker, and I have the jar. And I thought I could use this opportunity to mention, while I was doing this, I came across a really neat plugin for SBT called Assembly. Has anybody used Assembly for SBT? What Assembly does is, so just using pure SBT, you can create a jar, you can create a war of your application, right? But if you want to create like a final, I would call it like exe version. In this case, it's really like an executable jar. Assembly will obviously compile everything, package. It will also include the Scala library. It will include all your other like third-party libraries, and it will also, like, if you specify what is your main class, it would make that kind of in the meta file of the jar. It will create that as a exe version kind of. So it's just basically one command. You just say when you're in SBT shell, you just say assembly, and it just creates this jar basically here. So I'm going to start a worker. And it says I need to specify the bind address. So this bind address, that's that socket I was talking about. We basically have to say, okay, what is the socket that the worker is going to be on? And I'm going to say it's going to be localhost. But before that, so to just show you, so this, as I use assembly, I just thought like this is really nice if you have a need where, let's say you don't want to have, you want to send somebody some like Scala app that you developed, but you don't have that person. You don't want to have that person really like install Scala. This is the way to go, because if you see, once you have that assembly jar which has the Scala library inside, it can just be executed this way as like a normal Java jar. So let me finally start the worker. So it starts and it says 2 threads waiting for something to work on. So I'm using the Java system call to basically tell me what is the number of cores. Because if you're doing something, as you probably know, if you're doing something computationally intensive, it doesn't really make sense if you kind of spin a lot of threads. And I'm going to show that because I did some performance testing on Amazon EC2 cluster, and you'll see basically that it past a certain threshold, the more threads you spin, actually the slower your application will be. So I'm just going to grab these 2 guys as well. Okay, so now we have these 3 workers. So ideally, you would start these workers and kind of forget about them, because they should be able to accept any kind of function to apply and parameters, and you would never have to bring them down. One limitation of this of my implementation is whatever I have on the worker side, I call it the client side, those jars have to be on the class path of the workers, because these workers, they don't do the remote class loading. That would be really nice, but unfortunately it's not simple to implement. But you would basically just throw any function, doesn't matter what kind of code, and these workers would just apply that function. That's if you implement the remote class loading. So let me see here, go to, let's see, I have a couple examples. Here's like a really hello world example. So I'm just gonna show you the code really quickly. Okay, so here's the code. Basically what we're doing here inside the main method, I create a list of elements from 1 to 500, and then the operation on that list is called grid. What you get back is this kind of gridified list, which I think works perfectly because you as a programmer, as a user of the library, you want to be aware that this stuff is remote. You don't want to kind of confuse and think that this is local. And then you just do a regular map, like if you just want to increment every element from that, and you just print a result of that map operation, basically. So that's all there is to it. And I'm just going to run that. So you can see, basically 0 and Q did the load balancing. All these elements got sent to different nodes. The increment operation, which was obviously very fast, got implemented. And this is the result that we got back. So here's the list. So one thing to notice is that my original collection was the grid list, and I did a map, and now I got the list. And I assume, and hopefully someone will correct me, I assume that's bad, because when you do a map, you expect the same collection to get back. But this was the kind of a choice that I made. I thought it kind of makes more sense in this case to get back a list rather than, again, that grid list. So here's basically the resulting list, which has all the elements incremented. So let's get out of there and do a second example. Okay, so let's see what this is about. Okay, so this is just to show that you can do the same thing on two different instances of the grid list. So I have one list, and I gridify both of them. Then I have two instances. I have GL1 and GL2. And what's going to happen is I just want the map operation to be performed remotely on both of them in parallel. So I'm defining two threads. One thread is going to be multiplying every element by 2. The other thread is going to be finding those elements divisible by 7. So, and I just basically start the two threads and I wait for both of them to finish. So this is nothing terribly interesting, but just to show the fact that you can do concurrently on two instances. So I'm just going to start this and run. Same thing. So here is the result. And you can see here that these were performed concurrently because some of them are returning true and false Boolean, the filtering one, and the one that was multiplying is returning these results. So here's the first list, which has multiplied by 2, and the second list, which filtered out those divisible by 7. Okay. Let's go to the third example. In this example, I'm trying to show that you can now do concurrently multiple operations on the same instance of a grid list. So here I have originally one list, just one instance of a grid list, and inside 3 threads in parallel, we're going to be multiplying by 2, finding those elements divisible by 7, and also performing a flat map operation, basically trying to get the map which will have concatenated basically pairs of that element and then the square of that element. So here, again, just starting 3 threads and waiting for them to finish. Okay, so that's done. And to show you, so here's the first list. These are the ones, and you have no guarantee which one is obviously going to finish first, but the first one is divisible by 7. This is the flat map one, the second one with concatenated elements. And then the third one should have those multiplied by 2. Okay, but through these 3 examples, I didn't really show anything computationally intensive, right? These are really fast operations and everything was performed in a fast manner. So my last example is basically the one that is computationally intensive. and it has to do with the birthday paradox. Has anybody heard of the birthday paradox? Okay, so those who haven't heard, I have a question for you guys. So those who have, keep silent. The birthday paradox goes like this. In a room full of people, right? So let's imagine this room. How many people do you need so that there's a 50-50 chance that two people share the same birthday? Can you guess? So how many people do you need a room to have at least two that share the same birthday? Just do a wild guess.
23.
Okay, that wasn't fair. But the answer is 23. It's called a paradox because it's kind of non-intuitive. You know, you go like there are 365 days. You know, a lot of people say 180 something, but it really takes just 23 people to figure that out. And one way to solve this problem is using Monte Carlo simulations. So what you basically do is you just try to simulate. You just say, okay, you know, let me simulate that I have a bunch of people in the room. You generate some random birthdays, and then you just examine and check, okay, you know, do any two people have the same birthday? And you just repeat that like many, many times, and then kind of statistically you kind of prove, if I'm not mistaken, that that's basically how many people. And usually I believe it goes like, depending on the problem, probably like 10,000 times, 20,000 times, you do the simulation. Like those are called trials. In my example, I'm going to be doing a lot less because I don't want you guys to wait. But basically the problem that I was trying to solve is, okay, so it takes 23 people to have 50, to have the 50% chance. But then I was trying to see, okay, from groups of people ranging from like 2 people to 100 people, you know, what are the chances? And we're gonna see that in the output. So I'm just gonna go to that project. So this is the same thing with the assembly. So I'm gonna run this. It expects me to put the number of trials. So I'll just put 1,000 and let it run. So now you can see it's basically for every number of people, it's doing 1,000 trials and sending the results back. This takes a little bit more time, but I think it's going to be done. Yeah, we're about 90 something. Okay, so it took 21 seconds. So let's see, the result that we got back is here, and you can basically see with a small group of people the chances are really minor, and then around 23 we have 50, and then really to get to like 100, all you need is like 64 people. Okay, so that was a quick demo. Does anybody have any questions so far?
Sorry, 100 is chance of someone having a birthday.
Are you asking about the output?
Yeah, no, I was.
So basically, what this says is for 2 people. If you have just a room of like 2 people in the room, there's like 0.5% chance that they will share the same birthday.
You're rounding some very close to 100%.
Yes.
It may even be that in 100% of the 1,000 trials.
Right.
Actually did.
Yeah.
So.
Right. Okay. This is just show you some performance testing that I did, and along the lines that I was already talking about. So I did this using, obviously because this is computationally intensive, I used they're called like high CPU instances, the Amazon EC2 instances, and they're called CX1X large. I was doing 15,000 trials on a 4 and 5 node cluster. First thing I wanted to do is, I want to kind of prove, since it's really parallel, embarrassingly parallel problem, that if you throw in more nodes in the cluster, you're going to get better results. That is apparently true. And also, they both have sweet spots, and that's, it seems like 4 threads. Amazon says that these instances are 8 virtual cores. In my testings, it seems like they really are 4, but I'm not sure if I'm interpreting it right. I might be wrong. But basically, it shows that we get some improvements, and after that, if we use more threads than that, the results are just worse.